Hi class, welcome to Unit 4 Lesson 3. We'll be looking at interference of waves in 2 dimensions today. By the end of today's lesson, you'll be able to demonstrate understanding of interference of waves in 2 dimensions and investigate various factors affecting interference patterns. I know I've achieved these goals if I can describe in detail interference of waves in 2 dimensions and factors affecting interference pattern. Analyze mathematically the 2-point source interference pattern, solve problems related to these interferences, and apply this thinking and learning to the daily life problems. So interference is the process of generating a new wave pattern when 2 or more waves meet. To produce a fixed pattern, the interfering waves must have the same frequency and thus same wavelength, as well as similar amplitudes. Otherwise, the pattern will be indistinguishable. Patterns of interference also occur between 2 identical waves when they interfere in a 2-dimensional medium, such as water in a ripple tank. So there's 2 types of interference. So the first one, constructive interference. It occurs when waves build each other up, producing a resultant wave of greater amplitude than the given waves. And so as you'll notice, we have a positive crest here, positive crest for the wave 2, and when you add them together they build each other up, as well as same in the negative part here. They're making a greater trough. So for destructive interference, this occurs when waves diminish one another and they produce a resultant wave of lower amplitude than the given waves. And so when we have wave 1 from here, wave 1 is here, and we have wave 2 that's its negatives, its troughs meets the wave 1's crest. You're going to have destruction, and when you add them up together, you get one of destructive interference. Notice for both examples that we have the same wavelength and same frequency for the waves being added, as well as the result. So this following figure is a good example of showing interferences with 2 sources. So it shows 2-point sources vibrating with identical frequencies, amplitudes, and in phase. As successive crests and troughs travel out from the 2 surfaces, they interfere with each other. Sometimes you have crest on crest, trough on trough, and sometimes crest on trough, which produce both constructive and destructive interference. From the figure, these areas spread out from the source in symmetrical patterns, and notice how they're symmetrical and discernible, because if they didn't have these 3 things the same, then it wouldn't be a pattern. And so they produce nodal lines, which are the lines of destructive interference, as well as the areas of constructive interference. And so these bright ones would be crests, these dark ones would be troughs, and they can come from, like I said, 3 ways. Crest on crest will make a bigger crest. Trough on trough will make a smaller trough, a greater trough in the down direction, and crest on trough can produce either a crest or a trough, depending on which one is greater of the ones being added. And here we have a figure of more of a graphical version of it. Notice that this is, again, vibrating in phase with the same wavelength and frequencies. It's a symmetric pattern of hyperbolic lines which show destructive and constructive interference. So we have crests and troughs. Notice we have these nodal lines that show up on these lines, the nodes of the lines of nodes. That's why they're called the nodal lines for the lines of destructive interference. We also have these lines or areas of constructive interference. Show these ones, and we get super crests and super troughs when we have, if you take a look at this one, for example, you'll notice that we have a crest from one of the sources and a crest from the other, and they cross and they make a super crest. likewise, we have a trough from one, trough from the other source, and they line up and make a super trough. Whereas the nodes are where we have destructive interference, and we have a crest from one and a trough from another. And so we're getting destructive interference here, and so we end up with a node here. And so when they all line up, we have a nodal line. And that's why we have the areas of constructive and destructive interference. So what factors in affecting an interference pattern? This pattern will remain stationary as long as three things don't change. The frequency of the two sources, the distance between the sources, and the relative phase of the sources. When the frequency of the source is increased, the wavelength is going to decrease, bringing these nodal lines closer together and also increasing their number. And if the distance between the two sources is increased, then we have the number of nodal lines will be also increasing. So if the other factors are kept constant, but the relative phase of the two sources changes, this pattern is going to shift, as you can see from this initial to this final, with the number of nodal lines remaining the same. So for example, if S1 is delayed, the pattern will shift to the left of the right bisector. So this is our right bisector, right? Bisects this line at a right angle. And so if this is our before, when they have the same relative phase. So the idea of relative phase is the relative difference between two waves at certain intervals. So if it's measured at a certain frequency, a certain increments. So if it's like every pi by 2 or pi by 4, this is some just arbitrary function, but every certain amount you measure, you check basically the relativity between the two waves at that point. And so for this example, at each, these two are in phase, so their crests are lining up and their troughs are lining up. They have to be also the same frequency. So as you can see, if this is the two sources, at certain increments, they would be, for this case, say the initial is, this would be a relative phase or phase difference of 0 between the two. Just say because they're lining up crests and troughs, like just we'll say that is a difference of 0. But if we phase shift, say the orange one, by say 180 degrees or pi radians, if we shift it pi radians, and we all of a sudden we would get a function, the same function, just being translated, something like if we did that and now have the crests of the green is the new orange, say the crest of the green orange function is lining up with the blue opposite now, so we have a crest of the new function, a trough, a crest, and a trough. We're going to have a new net wave here. It's going to be destructive interference, right? Instead of two waves lining up and making a super, we now have the blue plus the new green destructing it, so it would be a lower net wave, something like that level. And so this shift amount that we've moved this point to this new point, this is our phase shift for the orange wave. And so the relative phase between the two we said was 0, and now if we've shifted 180 degrees, we now have, you could say, a relative phase difference between the two of pi radians or 180 degrees. And so if we shift these waves, if we shift, we're essentially shifting the timing of the wave. So if we're shifting it like this, we're kind of saying, okay, we're gonna turn the wave emitter on when the other one is producing a trough, and so this essentially creates new interference patterns, and for this case it's shifting the pattern to the left when we do a phase shift for these two sources, or delay S1 by pi radians. We get a pattern shift this way because you're essentially moving and changing how the interference stacks up. So the math in these kinds of scenarios tells us a lot of extra information. So it's useful because it allows us to measure the wavelength. So consider a ripple tank interference pattern produced by a pair of S1 S2 sources. We're going to say they're vibrating in phase and separated by 3 wavelengths. There are an equal number of nodal lines on either side of the right bisector. These lines are numbered 1 and 2 on both sides of it. So again, right bisector, nodal line 1, nodal lines 2, 1 on each side. So for any point P on the first nodal line, which is here, the difference in path length from P1 to S1 and from P1 to S2, so the difference with this one and this one's path length is half lambda. And for any point P2 on the second nodal line, the difference in path is 3 over 2 lambda. Which is here. So if we take a point P1 like we saw on one of the first nodal lines and connect it to each of the two sources by the lines P1 S1, P2 S2, or P S1 as in the figure, we see P1 S1 would be 4 lambda. And P1 S2 would be 7 over 2 lambda. The difference between these two distances is called the difference in path length. So P1 S1 minus P1 S2 equals half lambda, as we said. And likewise, he said the relationship holds for any point on the first nodal line on either side of the right bisector. When we measure in the same way the difference in path length for any point P2 on a nodal line second from the center, so second nodal line, we find that the difference between them is 3 over 2 lambda, which is what we said. And so if we keep doing this, we continue this and find a general relationship for a point P on the nth nodal line. And so we can say that Pn S1 minus Pn of S2 equals n minus half lambda. And this was also just equation 1. And so we have this nice equation, the nth nodal line, again, just meant equation 1. So we can use this relationship to find the wavelength of interfering waves in the ripple tank by locating a point on a specific nodal line, measuring the path lengths, and substituting in equation 1. So the difference in path length explicitly is in an interference pattern like this. It's the absolute value of the difference between the distance of any point P from one source and the distance of the same point P to the other source. again, that's from here to here, and from here to here for any nth nodal line. But if the wavelengths are too small or the point P is too far away, the difference in the path length is too small to be measured accurately. So we need another technique if we're going to do it this way. So in this example, if we have Pn here normally, and we're to move it so far off away that it makes Pn way out here somewhere to S1 and Pn S2. It's so far out that they are essentially parallel. It's considered parallel. How are we supposed to measure it if we can't see it off if it's out of a reference point? So in this case, the line here, if we pick this point here, AS2 forms a right triangle, and with both of these lines. And so once we have this right triangle, we can measure this distance, difference in paths with our angle here, theta, because we have a right triangle now. And why did we pick A here at this point is because if you do turn your viewpoint, you can see that if these two lines are considered parallel and they keep going that way, but it ends here and here, then this line at point A is this distance here is the difference between, it's this much longer than PNS2 line. If you turn your head, you can see that they're parallel, and when it stops at S2, this point here, when it stops, keeps going, this S1 line keeps going up until S1. You can see that it's that much longer, and so that's what we're looking for. We're looking for the difference in the two paths. And so we do this using sine. And so when we look at the right triangle, sine theta here is going to be opposite over hypotenuse. So that's AS1 over D. And then we rearrange, bring sine theta n to the other side. And we notice that AS1 is equal to PNS1 minus PNS2. Why is that? Well, it's just what we said. The difference between the paths, PNS1 and PNS2, is literally from A to S1. It's this distance here that what we're totally interested in. And so by putting that in and combining equations 1 and 2, one from before, we sub in for this. We sub in our n minus half because that's equal to PNS1. And since this, all of these are equal, we can put in the n minus half lambda from up there. And if we rearrange it for sine theta, we have this formula. And this is where theta n is the angle for the nth nodal line, lambda is the wavelength, and d is the distance between the sources. So we now can get that value. In the ripple tank, it is relatively easy to measure the angle n. The measurement is not, however, easy for light waves, where both the wavelength and the distance between the sources are very small and the nodal lines are very close together. So we can use this instead. So let's take a look at a problem. Two identical sources, point sources 5 centimeters apart, operating in phase at a frequency of 8 Hz, generates an interference pattern in a ripple tank. A certain point on the first nodal line is located 10 centimeters from one source and 11 centimeters from the other. What is the wavelength of the waves? And B, the speed of the waves. So let's draw this out what we were looking at before. We had our right bisector and our sources line. S2, S1, and we had a, say, a nodal line that was like this. Oops, n equals 1. And we had a point on the nodal line, P, because we said it was the first nodal line. And so that makes, let's get it a little clearer. A little straighter, but and so we're told that a certain point on the first nodal line is located 10 centimeters from one source and 11 from the other. And so this makes sense if this is 11 and this is slightly closer, it's 10. And we know that they are 5 centimeters apart. So that's really this distance. And what's the wavelength? So we have our PS2 is 10, as you can see this line from the diagram. And we have our PS1 is 11. So you write those down. The distance between the two is 5. So we have our D. We're given a frequency of both. Remember, they're both in phase. They have the same. And we want to know for part A wavelength and B the speed of the waves. So if we go back to our formula, the combining one, this one, we have most of the information here. So this one is suitable. And so we say PS, the absolute value of PS1 minus PS2 equals n minus half, all multiplied by lambda. And so we have this, we know this. Do we know n? We do. First nodal line, so it's n equals 1. And we're just left with lambda. And so we plug in our values, our units match, we just have to rearrange for lambda. And then we're left with lambda is 2 centimeters. And so once we have our wavelength, it's very easy to get speed from our universal wave equation. V equals f lambda. We have our frequency. We just found out the wavelength, so very simple to find out the speed. Plug in our values, and we get 16 centimeters per second. And that's going to be the end of the lesson today.